Here's the frame I got to work with, or if I don't like it, I can build one to do the same function. Question is, could I save some weight? Well, I don't know, 28 pounds, 4.2 ounces. If I'm going to use this frame, I ought to have some idea if it's as heavy as it has to be. Otherwise, if I could make something half the weight, I could save maybe 10-15 pounds, and the bike would perform all that much better. So to do that, I'll need to have some sort of a basis for judging how stiff the bike is for so much load. But to do that, I need to know how it's loaded, and loaded during a corner, because that's what I'm interested in. So what it comes down to is I need to know how the bike is loaded during cornering. And to know that, I need to start at the basics, which is, why does a motorcycle stand up in the first place? Alright, we're going to investigate why a moving bike stays upright, but a stationary bike does not. So here we have a stationary bike. We will confirm or deny that it does fall over. Confirm. Here is a diagram of the falling bicycle. Gravity is causing the center of mass to accelerate downward. The frame, however, supports the center of mass as it follows a circular path to terra firma. The compressive force in the frame balances the weight of the bicycle and the acceleration. That acceleration has an x component and a z component. This compressive force is balanced at the roadway by a normal force and a side force, W theta, which increases with the angle of tip. This diagram is also valid if the bike is moving. But there's one thing that has changed. The roadway is no longer fixed at one point, and this camber force causes the bike to move in the same direction that it is falling. So this W theta now balances the acceleration in the x component, so the bike is just moving sideways instead of falling. Basically, it moves in the same direction that it would fall, therefore it doesn't fall over. A top view of the bike shows that the bike has a component in the y direction, which in the other diagram was the x direction, and the forward direction. This little Vy here is the velocity it's gained when it started out tipping and moving sideways. The main component is its speed in the forward direction. The bike now has a velocity that is no longer aligned with the frame. It's actually shooting out into the right. And this has an effect on the slip angles. The plane of a wheel is not aligned with the direction it is traveling. The resultant angle is called a slip angle. A side force, roughly proportional to the slip angle, pushes the wheel in the direction it is steered. This is a familiar notion to anyone who drives a car. Turn the wheel to the right, the car goes that way. The same force steers a bike, but not in the same way. The force at the front tire causes that wheel to align with the direction of travel. Since the front end has a swivel to allow this, the front slip angle tends toward zero. There is no swivel at the rear, and the slip angle there creates a force that pushes the rear wheel in the negative x direction. A steering moment then exists that turns the bike toward the fall, bringing the center of mass over the base. The bike's tendency is to stay upright and moving more or less straight ahead. To guide a bike through a corner, we overcome this tendency. Lean into the turn and use the handlebars to prevent the front wheel from following the new direction. It is not necessary to turn the handlebars to the left, but a negative torque is required. Lean and handlebar control are needed to reach the desired angle, where camber forces match lateral acceleration. Where camber forces are providing the cornering power, it's an easy loading for the frame. The normal force and the side force combine to pretty much send a vector straight up the frame, so it's basically like adding a little more weight to the frame, which the frame is well designed to handle. So this condition is not interesting. What we want to think about is that period of time entering and leaving the corner, where everything is in transition and the slip angle forces are greatest. Here is a finite element model of a swing arm similar to a 250 Ducati narrow case design. Consider with a 10-pound force at the contact point on the rear wheel, the effect on the swing arm. See, there's a twist in there which results in about an 0.008 of an inch shift at the tire contact point. The side load also has an additional 0.002 shift just from pushing this sideways, for a total of 0.010 of an inch deflection due to a 10-pound side load. The same loading is transferred to a model of the frame. There's an additional moment because of the 17.5-inch long swing arm that produces a 175 pound moment around the center column with forces acting at the pivot shaft. And there's also the same load as at the rear axle, the 10-pound side load and the 120-pound twisting moment. This frame is made up of 3D solid elements, and the engine has been replaced by a single solid block to roughly approximate the same stiffness as the engine and save a lot of work trying to reproduce that. The result is we can see quite a bit of twisting happening around the head. The final effect of displacement at the rear contact point is 45 thousandths of an inch, which, adding the 10 thousandths of an inch contribution from the swing arm, brings us to 55 thousandths. There's also going to be some bending that occurs in the wheel, and we'll address that. I've set a motorcycle wheel, and this is off a 250 or 350 wards. I set it in the mill here, and on one side I've set a 16-pound block of aluminum, and on the other side I've put a dial indicator, and it's reading about 0.08 of an inch deflection. So this is about the same loading, about 120 inch-pounds, as the analysis. And the wheel is definitely going to be more flexible. It's got a WM1 rim instead of a WM3, and but other than that, it's fairly comparable, and I've got an 0.08 deflection for a 120 inch-pound moment. I have here a paper called Research Note: The Influence of Frame Flexibility on the Lateral Stability of Motorcycles by R.S. Sharp, Journal of Mechanical Engineering Science, Institute of Mechanical Engineering, 1974. Sounds pretty promising. Mr. Sharp says that torsional flexibility will affect the stability of the motorcycle, and he claims below 2,000 foot-pounds per radian stiffness, the bike would be a very dangerous bike. Between 2,000 and 8,000, he sees increasing stability with increasing stiffness. Above 8,000, he doesn't see any further benefit. So for my project, I'm looking at a somewhat smaller bike than what he's considering in his model. He has, I believe, 550-pound bike and rider, and I'm looking at maybe 400. So to this point, I've got a stiffness of the frame in the area of 5,000 foot-pounds per radian, and I would like to see that be a little stiffer. So in part 2, I'm going to look at ways of doing that and consider how different frame designs might meet the requirements, and also look at the bending stiffness, because it seems to me that is also as important.